All right, we're back. In previous videos, we've talked about risk aversion. We've defined risk aversion in the context of expected utility theory. While we were talking about expected utility theory, we also talked about loss aversion. We've talked about skewness and kurtosis. Know something that the textbook stops at the mean or the expected return and the standard deviation. They don't continue to talk too much about skewness and kurtosis. However, in the context of expected utility theory, when we talked about loss aversion, uh, I showed you some data about portfolios based on these ideas. It seems that loss aversion might be priced in stocks, so I think it's important. However, going forward, we're going to take the traditional or the standard approach, and we're going to assume that the only thing that investors care about are means and variances, means and standard deviations. Okay. So, from expected utility theory, we've defined risk aversion to mean that an individual will only take the gamble if the expected return is greater than the certainty equivalent. If you don't understand what I've said just then, go back and review the videos, the previous 3 videos. I think that will be useful. A risk-neutral individual will take the gamble if the expected return is equal to the certainty equivalent. That is, a risk-neutral individual is indifferent between gambling or the certainty equivalent. Okay? A risk-seeking individual will only accept the gamble if the expected return is less than the certainty equivalent. That is, the risk seeker in the traditional context or the traditional definition gets some sort of utility out of engaging in risky behavior. All right? So these are the definitions that we'll use. We'll ignore loss aversion for now. However, we're going to talk about this utility function that the CFA has on its exam. The CFA utility function is that expected return. Look, the utility of an investor is the expected return minus 1/2 A times sigma squared. Okay, everything has been defined here except A. We'll call A the coefficient of risk aversion. Okay, we'll call A the coefficient of risk aversion. We'll assume that all people have some level of risk aversion, so we'll assume that A is positive or at least non-negative. Okay, we'll assume that it's positive. All right, we know what the expected return of the investment would be or how to go about calculating it, and we know what the volatility or the sigma or the variance here, the sigma squared, would be of the asset. All right. What we want to do is we want to develop some more intuition, some economic intuition for how this might look. All right. Let me scroll down here and look at what I've done. I've just taken the utility function and I've transformed it so that the left-hand side is the expected return of the investment, and I've retained risk or our measure of standard deviation on the right-hand side. All right? And now what I can do is I can look and see what that might look like if I had the expected return on the left-hand side or the y-axis and sigma on the right-hand side or on the x-axis. Okay? So let me do this real quick. I'm going to take the partial derivative of this new function that's been algebraically transformed. I'm going to take the partial derivative with respect to risk. So I'm trying to develop what is the relationship between expected return and risk look like. And you can see that if I take the partial derivative with respect to sigma, I'm left with A, the coefficient of risk aversion, which is assumed to be positive here, times sigma, which I know is positive, right? Sigma is calculated as the squared difference, and therefore because it's squared, it will always be positive. And so the relationship between expected returns and our measure of risk is going to be positive. Notice something. If I take the second derivative of the expected return with respect to sigma, the second derivative is only A, the coefficient of risk aversion, and it also is positive. Okay? Let me explain what that means intuitively. So I know that the relationship is upward sloping between expected return and risk. So I should get an upward sloping curve. But because the second derivative is also positive, it's increasing at an increasing rate. Does that make sense? So this is my indifference curve here, and it's convex. So while a risk-averse individual's utility function over wealth is concave, recall that from the previous videos, the indifference curve is convex. And in fact, the more the more the risk aversion coefficient, so the greater A, the more risk averse an individual is, the greater this convexity is. Okay? So think about this. Which quadrant? So I've broken the YX domain into 4 quadrants, quadrant 1, 2, 3, and 4. Which quadrant would you prefer to be in if you're risk averse? Right? Hopefully you answered it's quadrant 1. You want the highest expected return for the lowest level of risk. Okay? You want to be up here in quadrant 1. The more risk averse an individual is, the greater the convexity of this indifference curve is. Okay, so let me explain what this might look like. Let me just grab another line here. So let's say this first line is investor A. He's kind of convex. He's kind of risk averse. Okay, here might be investor B. They're a little bit more convex. You see how we're trying to get to oh, what have I done here? Sorry. So the second indifference curve is investor B. Here's investor C, and this investor C, they're super risk averse, and therefore they experience a lot of convexity. Does this make sense? Hopefully this idea is showing you that what we're trying to do is get to quadrant 1. And the level of our risk aversion is going to drive how quickly we try to get to quadrant 1. Okay? So hopefully using the CFA utility function, this exercise has helped you understand how risk aversion affects the indifference curves, at least the convexity of those indifference curves. And the convexity of those indifference curves depends on the level of risk aversion.